Welcome to the Deep Dive. Today, we're taking a deep dive into the world of cloud databases, focusing on a truly fascinating system called Taurus. Many of you are probably already navigating the complexities of cloud-based databases, or at least considering the move. And what's universal across the board is the urgent need for services that are lightning fast, always available, and, well, incredibly cost-effective. The challenge we often see is that when traditional databases are simply lifted and shifted into a cloud environment, they frequently stumble on these very goals. They can become resource hogs, leading to significant waste and frustrating limitations on how much you can scale. Our mission for this deep dive is to truly unpack how Taurus steps up to these challenges with an architecture that's not just different, but fundamentally reimagined.
It's a critical topic because, as the groundbreaking research from Huawei Research Canada clearly highlights, an ideal cloud database service isn't just a wish list, it's a necessity. Such a service needs to be supremely available, virtually maintenance-free, capable of scaling out automatically without effort, delivering top-tier performance.
And all at a low cost, right?
Exactly. Low cost, where users only pay for the resources they actually consume. The paper meticulously details how Taurus was engineered from the ground up to meet these precise needs, marking a significant departure from merely trying to run existing database software in a cloud wrapper. It's about building for the cloud, not just in the cloud.
That's a powerful distinction. So let's unpack this core idea that really sets Taurus apart from the crowd. We know a lot of companies are migrating to cloud database as a service, or DBaaS offerings, but what often happens is they take battle-tested on-premise database software like MySQL and simply run it on virtual machines in the cloud. And our source material reveals just how incredibly wasteful that can be. Picture this scenario, as the paper vividly illustrates: a typical MySQL cloud deployment designed for high availability. Well, it might maintain 3 copies of a database.
Standard practice for redundancy.
Right. But then, each of those instances typically stores its data on virtual disks, which themselves, for reliability, often replicate data another 3 times across different storage nodes.
So you end up with...
If you do the math, yeah, you could easily end up with 9 complete copies of your entire database. Think about the implications.
That's huge. Enormous waste in storage space.
Exactly. And massive network bandwidth consumed by all that replication traffic, and CPU cycles constantly churning just to keep everything in sync.
It really adds up.
And if you want to scale out by adding more read replicas to handle growing query loads,
That gets slow and expensive.
notoriously slow and expensive, because each new replica requires yet another complete independent copy of the database to be spun up and populated. It's a multiplication problem that quickly spirals out of control.
What's truly fascinating here is how Taurus, following a similar philosophical path to pioneering systems like Amazon Aurora and Microsoft Socrates, fundamentally addresses this by separating the compute layer from the storage layer.
Okay, compute and storage separation. What does that really buy you?
Well, the compute layer handles all your queries, your transactions, the actual logic of the database engine. The storage layer, on the other hand, is solely focused on data persistence writing and reading the raw data pages.
I see. So they have different jobs.
Exactly. This fundamental architectural separation is powerful because it drastically reduces network load between your database instances and your storage.
Less chatter.
Right. And it inherently improves scalability by allowing these two components to grow independently. However, Taurus takes this separation a critical step further, making some unique architectural choices that set it apart.
How so?
Unlike some systems that might have multiple intermediate tiers or proxies, Taurus physically separates the database system into just 2 distinct tiers: that compute layer we just discussed, and a custom-built storage layer. This minimalist 2-tier approach is designed to minimize the amount of data sent across the network.
Less data flying around.
And crucially, reduces request latency to just 1 network hop on the critical paths for most operations.
Just 1 hop. That sounds significant for speed.
It is. That single hop is a significant factor in its performance.
That distinction, the single network hop, really underscores how deeply optimized Taurus is. But here's where it gets particularly innovative with Taurus's design. It introduces a novel approach by differentiating between how database logs and database pages are handled at the storage level. Most traditional databases treat these very differently. Let's simplify this. Think of database logs as the meticulous, sequential records of every single change, every transaction, every modification to your data.
The audit trail, essentially.
Kind of, yeah. These logs are absolutely crucial for durability. If your system crashes, you rely on these logs to reconstruct your database to its last consistent state. They are append-only, written in a continuous stream.
Okay.
Database pages, in contrast, are the actual data blocks, the physical manifestation of your tables and indexes. Accessing these pages is typically random.
Like jumping to find a specific piece of information.
Right. You might jump to any part of the database to read or update a specific record. The paper astutely notes that these fundamentally different access patterns, sequential for logs versus random for pages, make it incredibly inefficient to use the exact same underlying storage mechanisms for both.
Trying to do so forces compromises in either speed, cost, or complexity. This observation raises an important question. How does Taurus elegantly optimize for these inherent differences?
Right. What's their solution?
Taurus addresses this by creating dedicated log stores, specifically for log data, and distinct page stores for database pages.
So separate storage for logs and data pages.
Exactly. This isn't just a logical separation, it's an architectural one that allows each component to be optimized for its specific workload.
Let's dig into the log stores first then.
Okay. Their primary mission is to ensure absolute durability for your transactions. When a change happens in the database, the log records representing that change are immediately written to any 3 available log stores chosen from a large distributed pool of servers.
3 copies of the log record.
Yes, and a transaction is considered definitively committed and durable only when all 3 of those selected log stores report a successful write.
All 3 have to confirm. What if one is slow?
Good question. If one log store happens to be slow or unresponsive, the write is swiftly redirected to another available log store in the pool. This ensures incredibly fast writes and practically 100% write availability in a large cluster, assuming only uncorrelated failures, meaning no single event takes down multiple independent log stores simultaneously.
Okay, that makes sense for availability. What about reading the logs?
Log reads, on the other hand, are relatively infrequent, primarily used during recovery, and they benefit greatly from the simple FIFO, first in, first out, memory cache, ensuring quick access when needed.
Got it. So log stores are for durability and fast writes. What about the page stores?
So the page stores. These are designed specifically for serving those page read requests and applying the committed log records to update the pages themselves. The architecture cleverly divides a database into small, fixed-size slices, each about 10 gigabytes.
10 gigabit chunks, okay.
And each of these slices is then replicated to 3 distinct page stores for both durability and availability. So if one page store goes down, you still have 2 others holding that data.
Still 3 copies, but now for the data pages split into slices.
Correct.
When the database master modifies a page, it assigns a monotonically increasing logical sequence number, or LSN, to that page, like a version number for the page.
Pretty much, yeah. This LSN acts like a unique timestamp or version number for every change. What's crucial here is that page stores must be able to recreate any version of a page requested by the database front end.
Any version, even older ones.
Yes, including older versions, which is incredibly useful for lagging read replicas that might need to catch up to a specific point in time, or for consistent snapshots. This versioning capability is a cornerstone of how Taurus manages consistency across its distributed storage. The key architectural difference from traditional quorum-based replication models, where a majority of replicas must acknowledge a write for consistency, is that Taurus does not need a majority of page stores to be involved in each read or write operation for pages.
Wait, how does that work? Don't you need a majority for consistency?
That's the clever part, because strong consistency for the logs is already guaranteed by the log stores.
Ah, the logs are the source of truth.
Precisely. And because of the page versioning with LSNs, the page stores themselves can operate under an eventual consistency model.
Eventually consistent, so they catch up over time.
Exactly. They will eventually reflect all committed changes, but not necessarily instantaneously for every single write. This design choice significantly improves service availability and read performance, while still using only 3 data replicas per slice, which inherently minimizes storage costs compared to systems that might require 5 or more replicas for strict quorum-based consistency on data pages. It's a very smart trade-off that leverages the strengths of the log store.
So with all these innovations, what does this truly mean for real-world performance? The paper presents compelling numbers that are quite striking.
They really are.
Taurus can achieve up to 200% higher throughput than MySQL 8.0 running with traditional local storage.
Double the throughput.
And its TPCC performance, which is a widely accepted industry benchmark for transactional databases, can be 160% better than Amazon Aurora's published results.
Those aren't incremental improvements. Those are paradigm-shifting gains.
Definitely. So what's behind that?
This dramatic improvement isn't just one magic bullet. It's attributed to a combination of meticulously engineered factors, beyond the highly optimized one network hop design we discussed earlier.
Right. The single hop.
One of the most significant contributors is that Taurus page stores exclusively use append-only writes.
Append only, like just adding to the end.
Think of it like adding entries to a continuous ledger, rather than constantly erasing and rewriting entries in random places. This approach is intrinsically 2 to 5 times faster than traditional random writes.
Because you avoid seeks and stuff.
Exactly. It avoids complex disk-seek operations and write amplification. Moreover, it significantly reduces device wear for flash storage, extending the lifespan of expensive SSDs.
That's a nice side benefit.
It is. This simplifies consistency algorithms dramatically and makes snapshot generation incredibly efficient, almost a side effect rather than a complex operation.
And what about read replicas? They're absolutely crucial for scaling out read-heavy workloads in modern applications.
It's a huge part of cloud database usage.
Yeah. The paper reveals that Taurus not only supports a large number of read replicas, but it also manages to keep the replica lag, the time delay between the primary database and its replicas, under an astonishing 20 milliseconds, even under very high load.
Under 20 milliseconds. That's incredibly low.
To put that in perspective, it maintains lag below 11 milliseconds at a staggering 200,000 writes per second. That's near real-time synchronization.
Wow. How do they achieve that?
This exceptionally low lag is a direct result of another ingenious design choice. Taurus read replicas don't get their updates from the master database directly.
They don't. Where do they get them?
Instead, they receive updates straight from the log stores.
Bypassing the master entirely for replication data.
Completely. This prevents the master's network interface from becoming a bottleneck as read workloads scale. It distributes the traffic evenly across the highly scalable storage layer,
Spreading the load.
which in turn allows for a truly massive number of read replicas to be added without degrading performance. Imagine building applications that rely on fresh data, instantly available across hundreds of read instances. That's what this enables.
That's game-changing for read-heavy apps. And this design also has profound implications for recovery, a critical aspect of any highly available system.
How does recovery work?
Failures of both log stores and page stores are designed to be largely invisible to user applications.
Invisible. Really?
Yeah, mostly. For a page store, if it experiences a short-term failure, the node can rapidly recover any missed log records by communicating directly with other page stores using a lightweight, efficient gossip protocol.
They just chat amongst themselves to catch up.
Kinda, yeah. They quickly exchange information about what they know and what's missing, ensuring rapid consistency.
And if a node fails permanently?
If a long-term failure occurs, where a node is permanently lost, it's gracefully removed from the cluster, and its associated slice replicas are automatically redistributed to other healthy page stores and rebuilt from existing replicas.
Self-healing, basically.
And if, in a rare scenario, data is missing from all page store replicas for a slice, it can still be entirely reconstructed from the durable log stores.
So the logs are the ultimate backstop.
Correct. This level of self-healing minimizes downtime and operational overhead.
At the heart of connecting the modified database front end to this highly innovative storage layer is the storage abstraction layer, or SL.
The ESL sounds important.
It is. Think of S as a sophisticated library or an intelligent intermediary. It completely abstracts away the daunting complexities of remote storage, how data is sliced and distributed.
All the messy details.
Exactly. The intricacies of recovery mechanisms and the synchronization of read replicas from the database engine itself. This allows the core database engine to behave much like it always has, but with the power of Taurus's underlying architecture.
So the database engine doesn't need to know how the storage works, just that it does work.
Pretty much. When the database master needs to persist changes, SIL plays a crucial role. It accumulates log records into a temporary database log buffer. The very first thing SL does is write this buffer to the active log store replicas to ensure that critical durability is achieved.
Durability first, always.
Right. Once it receives acknowledgement from the log stores that these records are safely committed, SAL then distributes these records to per-slice buffers and flushes them to the appropriate page stores.
Okay, logs first, then pages.
But here's a powerful optimization. SIL only waits for a reply from one page store for a given slice before it releases the buffer and allows the master to continue processing.
Only one page store needs to reply. Doesn't that risk losing data if that one fails?
Not really, because durability is already guaranteed by the log stores having all three copies. This just significantly speeds up write operations because it's not waiting for all three page stores to catch up.
Ah, I see. The log store confirmation is the real guarantee. Waiting for just one page store speeds things up dramatically.
Exactly. It's a masterful balance of speed and reliability.
The SLL also plays a pivotal role in maintaining consistency across the entire distributed database through a mechanism called the Cluster Visible LSN, or CVLSN.
CVLSN, Cluster Visible LSN, what's that?
This CVLSN isn't just any LSN. It represents a global point in time, a universally consistent state where all pages across the entire database are internally consistent, reflecting all committed transactions up to that point.
A global consistency point.
Right. SAL carefully manages this. It only advances this CVLSN when two critical conditions are met. First, the log records have been successfully written to the durable log stores.
Durability check.
And second, at least one page store for each relevant slice has successfully applied those log records.
Log durability plus at least one page copy updated.
Correct. This multi-layered approach ensures that page stores can always serve pages at an LSN equal to or greater than this global CVLSN, guaranteeing that any read operation will always see a consistent view of the data, even in a highly distributed and eventually consistent page store environment. It's how Taurus provides strong transactional guarantees despite its distributed nature.
This deep dive into Taurus has really showcased how a ground-up redesign of database architecture can yield truly revolutionary benefits in the cloud. By intelligently separating logs and pages, leveraging the speed of append-only writes, and implementing novel replication and recovery algorithms, Taurus manages to be incredibly fast, exceptionally highly available, and surprisingly frugal with resources.
It clearly demonstrates that thinking differently about fundamental database components and then fully leveraging the unique strengths of a cloud environment is the path to overcoming the inherent limitations of simply porting traditional database systems.
Yeah.
It's a testament to the power of cloud-native design.
So if you've ever found yourself grappling with the persistent trade-offs of performance, availability, and cost in cloud databases, consider how these ingenious architectural decisions in Taurus, like the distinct separation of log and page storage or the prioritization of append-only writes, could fundamentally reshape what's truly possible in cloud-native data management for your own applications.